quite a broad remit or brief for this meeting, and that was to, I think, set the scene as to how important the subsurface might be for low carbon in general. So not necessarily so much about geothermal, but I've clearly sort of read the runes and have added some geothermal in here. But it's an interesting question, you know, how much will the subsurface contribute to low carbon, to net zero, to decarbonisation? This is something I've had particular interest in. We've organised meetings and written papers and books about this issue. So it's something that I think geologists are thinking about. And what I propose to talk about is just three very quick and simple things. One is, how will the subsurface contribute to net zero? In broadest terms, what do we need to know more about as geologists? Again, in the most high level terms. And then a quick look into the future, if some of these subsurface technologies were to be realized and to actually work by, say, 2050. So it's quite a kind of broad view. So the first thing is, I guess nobody would really argue that there are quite a few things that the subsurface contribute to net zero. One is energy storage in the form of heat storage or compressed air energy storage, because one of the solutions for low carbon energy, of course, is more renewables, and therefore we need to be able to deal with intermittency better. So energy storage is an enormously important area, and engineers are looking at it from the point of view of batteries and other technological solutions, but geologists are also looking at it. Geothermal is an obvious solution, and that's something that we're talking about today. Something that's often forgotten about in the argument is how the metals and materials that we use for energy storage, for batteries, for example, or myriad of things that we need for low carbon, where we're going to get them from. And that's an important geological issue. So, for example, where is our lithium going to? I think someone's got their microphone on. Carbon capture and storage is an issue, obviously, which relates to, you know, what we do with the CO2, which we do have to emit because it's just something that we can't sort out. For example, cement factories or ammonia factories or coal mines, coal-fired power stations or gas-fired power stations. And of course, there's the hydrogen economy, which has got a lot of press recently because hydrogen is looked at as a kind of very long-range battery, if you like, because it's a great way of storing energy, particularly if you link it in with your renewables. So all of these use geoscience and subsurface heavily. And what do we need to know more about? Again, in the most broad, simple terms as geologists, and this is sticking to the technical issues, what is it that we need to do to make sure that these things work? Well, really thinking about this and having conferences about it, two things really come out very, very clearly. One is the fact that we need to understand confinement of flow, because so many of these technologies are about putting something down in the ground and making sure that it doesn't go anywhere. So for example, for carbon capture and storage or hydrogen. So we need to understand the confinement, how geology, how rocks, how they confine flow. But paradoxically, the other side is, of course, that at times we want technologies to allow increasing flow. So geothermal is an example of that. We want fluids, water to flow so that it gathers heat so that we can use it. So they're actually opposing views, but they do, or opposing kind of factors in the technology. So we do need to know this really well. Fluid flow in rocks is a really important issue here. And actually, to be able to do that, we need to understand rock heterogeneity much better. And rock heterogeneity is what most geologists do. And perhaps they don't realize it. It's all the work in sedimentology and mineralogy and everything that traditional geologists do. That's rock heterogeneity, how it differs as you move down section or across, and what might be ways that you could predict that change in heterogeneity. And of course, there's the basic fluids, flow, physics, chemistry, and biology. And I mention biology because, of course, biota has a role in the subsurface. We all know that films of algae and other biological materials can cause problems with fluid flow, for example. It's quite well known. So these are the really big issues that geologists need to tool themselves up with in order to make sure that these different technologies work. I'll just give you a few examples in a bit more detail. So this is carbon capture and storage, which everybody here will be familiar with. It's about taking CO2 from industrial sources and putting it under the ground. And it's a way that we could deal with some of the more difficult parts of the decarbonisation spectrum. But this shows you a complicated diagram about containment in the CO2 store. So we know now from lots and lots of work on this that there are many processes at work. There's migration of CO2 under aquifer flow. There's the trapping mechanisms. There's the fact that the CO2 fluids will react with the rock and numerous other issues that we have got a pretty good handle on here in carbon capture and storage particularly, but it's something that still needs work. So if you don't understand the containment in the CO2 store, then you're going to have problems kind of managing the process, but also perhaps in talking to the public about it, as we earlier discussed. Here's another issue, which is perhaps slightly more subtle, and this is about how you manage the large-scale use of the subsurface in relation to carbon capture and storage. But this could just as well be related to geothermal or any other use of the subsurface. The point is you have to use it optimally, and you could use it in the wrong way. You could, for example, in this case, decide to inject CO2 into a structure say in the subsurface of the North Sea, and find that by choosing that structure first, you invalidate structures around it by increasing the pressure beyond a certain point. And that means that you have to very carefully plan how you use subsurface structures. You have to understand in great detail the fluid flow. Otherwise, you will essentially sterilize areas without thinking. Of course, you have to think it in terms of how the surface might be used as well. So the seabed for wind farm applications, for example, and how you might interfere with gas fields if they're still operating nearby. So you really have to plan this properly. Otherwise, you could actually make a mess of it. It's just like any kind of planning at the surface that we would do to sensibly use our resources. We have to do it in the same way in the subsurface. And of course, also, it's interesting in vertical terms that you could sterilize a structure unknowingly below a structure you're injecting by, again, overpressuring it, because you aren't thinking about the fact that storage sites in CCS could be stacked. So this is a really interesting, subtle issue related to planning and optimal use of the subsurface. And finally, again, in carbon capture and storage, there's the issue of how you monitor. This is a complicated diagram that shows all the ways that you should monitor or could monitor CO2 in the seabed, below the seabed, in structures that you've injected. And this is really important, again, for managing the situation, but again, for public confidence in the technology, for public license or license to develop these things. And again, it involves an awful lot of science and understanding. And of course, it's the same for any of these technologies, where it be compressed air energy storage, geothermal, hydrogen storage, or CCS, or radioactive waste storage as well, or radioactive waste disposal. So all of these are tremendously important. So I think I've given you a rough idea of what the real upfront challenges are in terms of science and some examples. Let's now look into the future a bit. So I kind of conveniently divide onshore and offshore in terms of geoscience and decarbonisation, because they have slightly different dynamics, slightly different solutions, slightly different natural advantages, which means you get a different configuration. So if we first take a look at offshore, now this is really getting exciting. There's a great article and strategy document produced by the OGA, the Oil and Gas Authority, recently, who've sensibly begun to think about decarbonisation as opposed to oil and gas. And they think that the offshore could offer 30% of the emissions reductions that the UK needs by 2050, a really startlingly high figure. And the way they think that could be done is through lots of carbon capture and storage, so industrial decarbonisation of clusters, industrial clusters, an enormous expansion of wind. And of course, we heard the Prime Minister talking about that. And also this really interesting idea of blue and green hydrogen offshore. So making hydrogen from the blue method, which is essentially methane reforming, and also using electrolysis to produce green hydrogen. And that's a long-term store of, for example, renewable energy. And of course, you could also store some of the hydrogen in the subsurface under the North Sea, for example. So this is a really big and new idea, using renewable energy to generate hydrogen, which you can then use to store energy for the long term onshore. And we're talking about artificial islands where wind, CCS, hydrogen, and maybe underground storage of hydrogen takes place. Places out in the North Sea where you essentially generate a lot of the low carbon energy you need for industrial and modern Europe. This is more detail, and it's the only detailed slide I've got. This is from the OGA. It just shows how interesting the North Sea could get. So you've got electrification of platforms. So in other words, not using diesel to power platforms anymore. You've got carbon capture and storage. You've got green hydrogen being generated by renewables and being stored. You've got gas to wire, so actually generating electricity actually offshore on platforms using gas. You've got blue hydrogen, so generating hydrogen using methane offshore. And these large-scale energy hubs where you actually put everything together. This is what the OGA thinks could generate 30% of the savings that we need to get to net zero. It's a fascinating idea. What about onshore? Well, onshore's different. I mean, what we're looking at here is no CCS. Obviously, we could have hydrogen storage, but we have one big issue in onshore decarbonisation, and that's domestic heat. It's heat for houses, and people know about this better than I do on this call, and many people listening will know more about this. But essentially, we're looking at coal mine heating, which is something that we're really keen on, and that's something that Alison talked about just now. In cities that overlie coal fields, there's shallow aquifer geothermal, and there's shallow urban geothermal heat, so heat generated by the urban environment or by the industrial environment that we might use. And one of the great things about BGS is that we are pretty well kitted out to deal with all three of those issues of geothermal in the onshore. So as Alison described in detail, I actually watched her presentation earlier on. I hurriedly changed mine so that I didn't overlap too much. So essentially, as Alison said, the Glasgow Observatory is about coal mine heat and heat storage. Can we use heat in these natural kind of high permeability rocks that we've created to heat houses and buildings? And could that be done elsewhere in the UK? Could it be done in the United States and in Europe, where there are lots of cities that sit on coal mines because of the Industrial Revolution? In shallow aquifer heat, we're just about to open or in about a year, we'll be opening the Cheshire Observatory, which was something that was mentioned briefly by Alison. So this is really looking at aquifer heat and heat storage. We have an advanced array being developed with heat exchange devices, with very highly monitored and instrumented boreholes, with a whole suite of fantastic equipment, which will help us to understand the potential of, for example, the Sherwood Sandstone group, which we've talked about quite a lot. So this is the place where you can do your research to understand what the potential is for shallow aquifer heat in the subsurface in much of England, Scotland, and probably Northern Ireland as well. I don't know why that is. And the last one is the Cardiff Observatory, which is also part of UK GEOS, which is essentially looking at shallow urban geothermal heat. It's been running for quite a long time. There's lots of online data that you can get right now if you log on. And it's really looking at the complex geological environment changed by industrialization and urban growth. So I'm not sure if I'm on time, but essentially my conclusions are, if you didn't really know that the subsurface is vital for net zero, I would say it is. And geoscience really needs to get working with the engineers, because it's the engineers who are actually being mostly charged with this solution to this problem. Regrettably, I think the geoscientists aren't quite there. We haven't got quite the sort of leverage that the engineers have got, but we really need subsurface. And there are some fundamental geoscience questions that, I mean, we've solved many of them. We understand much about confinement and the free flow of fluids, but there are difficult parts of this that we don't get so well. And we're dealing with new fluids that we, maybe didn't know so well. So hydrogen is an interesting one. Offshore future is very exciting. I mean, we could be looking at a large amount of the Europe's energy being generated or being produced offshore. So and also CO2 being disposed of offshore, with an enormous increase in wind, with blue-green hydrogen, with CCS. And this is really aimed at industrial decarbonisation, big grid electricity, big storage. I don't know what percentage that could deliver, but these are base figures for UK's emissions for, I think, 2014. And it shows that the sorts of things we could contribute to are the business and industry and the power sector. And transport's more difficult, except for batteries, but I think a fairly high proportion of that pie chart could be delivered by geoscience if you factor in CCS and the blue-green hydrogen part, and aspects of wind as well, because we need to properly locate and use the seabed as foundations for wind turbines. The onshore future, well, I think we've got coal mine heat, we've got shallow aquifer heat and urban heat. And again, these could be mainly aimed at decarbonisation of domestic heating. And you can see homes there illustrated as a percentage of 13% of the CO2 emissions. But of course, if you add business buildings as well, it comes to about a third. So really you have, we could really be delivering a lot if we get our act together. We could be delivering, as geoscientists, quite a bit of this challenge to get to net zero by 2050. That's it.